Namaste students, welcome back to Rama Teaches You. Today we're going to do the chemical bonding and molecular structure, the next video. Okay, so in the previous video we had already finished up with the valence shell electron pair repulsion theory, which is also known as the Vesper theory. So in this video we are going to continue from the previous section. Okay, we did a lot of limitations. There were a lot of limitations in the valence shell electron pair repulsion theory. Why? Because it did not take into consideration the various different the new concepts that we had in chemistry, like the dual nature. Okay, the quantum mechanical model was not taken into consideration while developing the valence shell electron pair repulsion theory or the Vesper theory. So in order to overcome that, we have two different theories. We have the valence bond theory and the molecular orbital theory. Okay, so in this class most probably we are going to complete the valence bond theory. Okay, let's see. So, what is valence bond theory? Mm, yeah, okay. So, this theory was introduced by Heitler and London in 1927 and further improved by Pauling. Pauling is the same guy who gave us the electronegativity scale. Okay, he is the one who gave fluorine the minus the electron. What was the fluorine's electronegativity? 4, right? Fluorine's electronegativity was 4. He was the one who gave fluorine the electronegativity of 4. Now, and Slater in 1931. The valence bond theory came into picture because Vesper theory was unable to explain the geometry of simple molecules, okay, and had limited applications. It is based on the knowledge of atomic orbitals. We know that there are electrons that are present in the atom around the nucleus. They are present in various kinds of orbitals. Okay, so orbitals are what? Orbitals are places around the nucleus of an atom where the probability of finding an electron is the maximum. Okay, it is based on the knowledge of atomic orbitals, electronic configuration of elements, the criteria of overlapping of atomic orbitals, and the hybridization of atomic orbitals, and the principle of variation and superposition. Okay, we are going to understand each and every single line that I have just discussed below. Now, in order to understand the concept clearly, let us consider the formation of the H2 molecule. We know that there is a single bond that is present between the two hydrogen atoms, right? In an H2 molecule, there is a single bond that is present between the two hydrogen atoms. Consider the two hydrogen atoms A and B. So we are giving them two names, hydrogen A and hydrogen B. Okay, are approaching each other. Their nuclei Na and Nb and the electrons present in them are represented by Ea and Eb. So Na represents the nucleus of the hydrogen A. Nb represents the nucleus of hydrogen B. And both of them are surrounded by their corresponding electron clouds, Ea and Eb. When the two atoms are far apart, there is no interaction between them. But as they approach each other, some new attractive and repulsive forces begin to operate. So, what is the attractive force that is taking place? The nucleus of one will try to attract the electron cloud of the other. Similarly, the nucleus of the other will try to attract the electron cloud of the first one. Okay, that is where the attractive forces arise. Now, attractive forces between the nucleus of one atom and its own electrons. Of course, the electrons are held inside the atom via the what do you say, the attractive force between the nucleus and the electron. Okay, and the same goes for nucleus and the B part. Nucleus of one atom and electron of the other, that is NaEb and NbEa. Similarly, repulsive forces arise between the electrons of one atom, that is EaEb, the nuclei of two atoms Na and Nb. Now, the attractive forces tend to bring the combining atoms close to each other, whereas the repulsive forces tend to basically keep them apart. So, what is the repulsive forces? The repulsive forces are the two electron clouds that exist between the hydrogen A and the hydrogen B. Similarly, there is a repulsion that is existing between the two nuclei, Na as well as Nb. So these are the two repulsive forces that exist. Now, the repulsive forces are trying to keep the two hydrogen atoms apart, The attractive forces are trying to bring both the hydrogen atoms close to each other. So these two are balancing each other out. The place where these two balance each other out is what we call the formation of a bond. Are you able to understand slowly, Drupad? Okay. Now, experiments also reveal that the magnitude of the new attractive force is more than the repulsive force. This is what something that is crazy. Okay. The attractive force between the two atoms is always going to be greater than the repulsive force. That is the reason why bonding takes place. If both were the same, if the repulsive force were greater than the attractive force, no two atoms would actually combine with each other. Okay, the two atoms would always stay as far as apart as possible. Because nature made it so that the attractive forces overcome the repulsive forces, therefore we are having the bond formation. Understood? The puzzle is able to get completed because the attraction is greater than the repulsion. Understood? Okay. Now, experiments also reveal that the magnitude of the new attractive force is more than the new repulsive forces. As a result, the potential energy decreases due to the approaching two atoms. Now, the repulsion results in what? The repulsion results in a lower potential energy. Now, something that you need to take into consideration is that anything that exists in nature wants to have the least potential energy as possible. Always. It is always going to be true for that. You should have the least potential energy possible. Okay, and that is happening when there is attraction taking place. Okay, now let's look at this. Ultimately, a stage is reached when the net forces of attraction balance the forces of repulsion and the system acquires a minimum energy level. Okay, now the attractive forces and the repulsive forces. What are the attractive forces? The nucleus and the electron of the other, and the repulsive forces are electron electron repulsion, nucleus nucleus repulsion. Okay, both of them are going to balance each other out at a particular distance. Okay, now this is the state when the hydrogen atom are bonded together to form a stable molecule. Now when the two attractive and repulsive forces balance each other out, you get the bond formation. Bond formation finally becomes complete. The hydrogen molecule, the hydrogen bond is 74 picometers. So picometers means 10 to the power minus 12 meters. Now, the hydrogen molecule is more stable than that of the isolated hydrogen atom. Since the energy gets released when the bond is formed between the two hydrogen atoms. Okay, it is stable. So, ideally speaking, two hydrogen atoms, when they were not bonded together, they were at a higher energy level. Okay, but when they formed the bond, they became stable because some amount of excess energy that they had with each other, they released it while forming the bond. Okay, so when you want to break a hydrogen bond, you have to provide the same amount of energy to the bond to actually break them. Understand? Is this clear? Vipad, they were able to make the bond. Okay, yeah. So the hydrogen molecule is more stable than the isolated hydrogen atom since the energy gets released when the bond is formed between the two hydrogen atoms. The energy released during the formation of a bond is called the bond enthalpy. Okay, bond enthalpy is the amount of energy released when the bond is being formed, which is corresponding to the minimum in the curve as depicted in the figure. Conversely, 435.8 kilojoules of energy is required to dissociate 1 mole of H2 molecule. Okay, so Drupad, the atoms basically spent 1 mole of hydrogen atoms, sorry, 2 moles of hydrogen atoms became 1 mole of H2 molecule by giving away 435.8 kilojoules per mole of energy. Now, if you want to break them, you have to provide the same amount of energy. So, when the bond was being formed, energy was released. So, if you want to break the bond, you have to provide them with the same amount of energy. That is what we call the bond enthalpy. Okay, enthalpy means heat, enthalpy means energy. It is a form of energy. Okay, so you have to provide them with the same amount of energy that they released to break the bond. Okay, Now look at this. The potential energy curve for the formation of H2 molecule as a function of internuclear distance of the hydrogen atom. The minimum is the curve corresponding to the most stable hydrogen atom. Now can you see this? This 74 picometers. This is the region of 74 picometers. This is where what is happening? The potential energy is the minimum. When there is minimum potential energy, the molecule is more stable. Understood? Now, as the distance between the hydrogen atoms increases, what happens? The potential energy actually increases. It becomes less negative. Can you see this? This is the zero line. As the two hydrogen atoms move away from each other, what is happening? The energy is becoming more and more positive or less and less negative. Okay, now one more thing. If you try to bring the two hydrogen atoms closer to each other than before, then what happens? If they are brought even closer, what happens? There is the repulsion that is taking place between the two nuclei. Repulsion is happening here. Understood? So, repulsion means what? Sudden increase in energy. So, you cannot bring them very close to each other. There is a certain distance where you will have the potential energy to be minimum. If you bring them much more closer than that, then what will happen? The potential energy will just start to burst and increase. Okay, it will increase. The repulsion between the two nuclei will be very large. Therefore the overall potential energy will also be very large. Understood? So this is how the whole system works. Clear? Rupert, is this clear? Okay, let's move on. Orbital overlap concept. According to this concept, a covalent bond is formed by the overlapping of two half-filled atomic orbitals of valence shell having electrons with opposite spin. Okay, the greater the overlapping of the atomic orbitals, stronger is the bond formed between the two atoms. Okay, now two orbitals having electrons of opposite spin are overlapping on one on top of each other. Okay, and more there is overlap, the stronger will be the bond. For example, if I'm just holding this one finger, this bond between these two hands is not that great. But if I try to hold them like this, okay, with both the hands together, then the bond is stronger. Now the overlap is even more stronger. Now the overlap is even more stronger. Okay, the more overlap you have, okay, the more overlap you have, the stronger your bond will become. Clear? Is this 100% clear? Okay, now let's move on. Directional properties of bonds. The valence bond theory explains the formation and the directional properties of bonds in polyatomic molecules like CH4, NH3, H2O, etc. in terms of overlap and hybridization of atomic orbitals. Hence, it also accounts for the geometry of the resulting molecule. The valence bond theory actually gives us the various kinds of geometries that we are going to have. Okay, it takes into consideration the various shapes that were involved when we were talking about the Vesper theory, and it just basically overshadows that in the valence bond theory. One second. Since the strength of the bond depends upon the extent of overlapping, O orbitals apart from s orbital form bonds only in certain directions to give the maximum overlap. So we are going to discuss something known as the directional properties of bonds. Okay, how and why do they bond or overlap in such a way? They overlap in such a way so as to get the maximum amount of overlap area as possible. Okay, experiments have shown that H2S is a non-linear molecule with HSH bond angle to be 92 degrees. So HSH, H2S, hydrogen disulfide. Okay, so basically H2S or H2O, they were supposed to be what? The linear pair, right? They were supposed to be linear pair or a linear molecule, but because of the presence of the lone pair of electrons, what happened? The lone pair repulsion and the lone pair bond pair repulsion forced the bond to decrease its angle from 180 degrees all the way to 92 degrees. Now, Because sulfur has two lone pair of electrons, then the repulsion will become even more stronger. Right? We have already discussed this in the Vesper theory. Do you want me to explain this again? Do you understand this? Sulfur has six electrons, right? Do you want me to explain this once more? Oh, okay, fine. So, okay. When orbitals of two atoms overlap to form bond, this overlap may be positive, negative, or zero. It depends upon the sign and the direction of orientation of amplitude of orbital wave function of the atomic orbital. Now we know that the atomic orbital is what? Is based on the wave function of the electron around the nucleus of an atom, right? The atomic orbit, what is the wave function? Wave function represents the path the electron will take inside the atom, right? So now we have to discuss what a positive overlap, a zero overlap, and a negative overlap actually means. Now, for example, positive overlap takes place when two pz orbitals overlap along the internuclear axis. What is the internuclear axis? Now, so internuclear means between the nucleus. Okay. So you have a nucleus here. You have another nucleus here. So this length, this path is known as the internuclear path. Understood? Now, did you understand this? You have to understand this very carefully. There is something known as internuclear and then there is known as axial. Okay. So the positive overlap takes place when two pz orbitals overlap along the internuclear axis. The z axis is taken as a molecular axis by convention with the lobes of the same sign. Okay, lobes should have the same electronic this thing. Now, on the other hand, when two pz orbitals overlap along the internuclear axis with the lobes of opposite sign, so we know that there is in every single orbital how many electrons are present? There are two electrons present. One electron has a positive spin, the other electron has a negative spin. Okay, now if both the lobes were to be positive, then what would happen? Then the overlap would be considered to be positive. But if you have one overlap positive and the other overlap negative, then what will happen? On the other hand, when two pz orbitals overlap along the internuclear axis with the lobes of different sign, one positive and the other negative, it results in a negative overlap. This is because the lobes of different signs cannot combine. Okay, only the lobes having the same sign, that is the same what do you say, same direction of spinning electrons, the same sign can only overlap with each other. Okay, the different arrangements of s and p orbitals result in the positive, negative, and zero overlap are given below. Now, this is known as the pz lobe. Okay, pz, you know what the shape of the p orbitals are, right? You have the px like this, you have the py like this, and you have the pz on the z axis like this. Okay, now we have taken the pz orbitals. So what is happening? The pz has two lobes, one positive and one negative. Now if both the positive lobes are going to overlap with each other like this, then you have a positive or an in phase overlap happening. But if you have a positive and negative overlap taking place, then you have an out of phase overlap happening. Okay, now similarly you have the s, the p and the s overlap like this. Okay, the pz and the s, this is also another type of overlap formation. Next, you can have something known as a sideways overlap. Okay, this is what is used to form the pi bond. Okay, this is known as sideways overlap. So Drupad, what do you think? This is the head on overlap. What do you think, Drupad? In a head on overlap or in a sideways overlap, where is more area of overlap taking place? In the sideways overlap, right? No. Sideways overlap, there is not, it's just an illusion. The head on overlap is the area where maximum overlap takes place. Okay, I'll explain this to you in the coming slides. Okay, so this is the sideways combination. Okay, again you will have positive overlap, this will be negative overlap. So what is the difference between a positive overlap and a negative overlap? If there are two positive signs, okay, if the positive lobe overlaps with the positive lobe, you get a positive overlap. If a positive lobe and a negative lobe overlap with each other, you get a negative overlap. Understood? Next. Okay, this is another type of combination. See, the PY combination. Okay, this was what? The PX. This is PY. Okay, this is negative overlap. Again, then you have the PZ, the sideways S overlap. Okay, this is where there is least amount of overlap happening. Now, you may think that, sir, this there is some overlap here. No, there is no overlap here. Okay, because a p orbital and an s orbital need to have a head-on overlap for the overlap to take place. What have we learned about the electron density of a p orbital? The electron density of a p orbital in the center is almost zero, right? It's almost zero. There is negligible amount of electrons actually present near the center, right, for a p orbital, whereas there is a large amount of electrons that are present in the s orbital at the center. But since there is no overlap happening, there is no sharing of electron that is actually taking place, what happens? We call such a type of overlap as zero overlap. Okay, the name should actually give you the clue. When no overlap happens between the two orbitals, we call it zero overlap. Understood? Clear? Now, you you can ask me, why does the px and the py never overlap each other? The px of one and the py of the other cannot overlap each other because their orientations are different. Okay, px looks like this and py looks like this. Okay, the only place where they both meet is the center, and in the center there is no electrons to begin with. Therefore, you cannot have a sideways or a head-on overlap between two orientations of the p orbital. The py and the py can overlap. The pz and the pz can overlap. The px and the px can overlap, but two different directions cannot overlap. Understood? So there is zero overlap that is taking place. So we have discussed three types of overlaps. One is called the positive overlap, one is called the negative overlap, and a third is called the zero overlap. Okay, now the sideways overlap and the head-on overlap is going to be of much importance to us because this is how atoms form bonds. Okay, there is a head-on collision that takes place between the two orbitals of two atoms, thus resulting in a head-on overlap. Okay, and because of the head-on overlap is what, then and only then you have the sideways overlap taking place. Okay, I'll explain this to you more in more detail as the topic comes. Okay, now the types of overlapping and the nature of the covalent bond. Depending upon the types of overlapping, the covalent bond may be classified into two types. One is known as the sigma bond. Okay, sigma, that is the main bond that you have. It's called the sigma bond. The other is called the pi bond. Okay, sigma bond is a result of head-on overlap. So basically, these are the different types of sigma bonds that you can have. This is sigma, this is also sigma, this is sigma, this is also sigma. These two are, and this and this and this and this, all of them are not these two because there is no overlap actually happening here. Okay, all of these are examples of the pi overlap. Okay, let's go through them in more detail. So, the sigma bond, this type of bond is formed by the end to end head on overlap of bonding orbitals along the internuclear axis. So, the sigma bond will always be formed in the axis between the two nuclei of the two atoms. Okay, if you have a nuclei here, you have a nuclei here, the sigma bond will lie in the axis of the two nuclei. Now, this is also known as a head on overlap or the axial overlap. This can be formed by any one of the following types of combination of atomic orbitals. You have the SS overlapping, the SP overlapping, the PP overlapping. That is all that you have to do in your, at least in your level of curriculum. Okay. Now, in SS overlapping, what happens? As the name suggests, two S orbitals are coming in head-on collision. Okay, their orbitals are overlapping with each other, thus forming what? They're forming an SS overlap. Now we know that what is in the center of the S orbital? What is here, Drupad? The center of the S orbital is where the nucleus is. Yes, exactly. The center of the s orbital is where the nucleus is actually present. Okay, now we can say that because in the center the nucleus is present, okay, the axis, the axis between the two nuclei is where the bond is being formed. This is known as the internuclear axis. Okay, so this is the internuclear axis. There is an overlap that is taking place here. Okay, this is how the overlap actually takes place. Now, what about the PPSP overlap? Again, you have an s orbital and a p orbital. Both of them are basically overlapping each other to form an sp bond or an sp overlap. Next, you have the pp overlap. It occurs between the half filled, the half oh the half filled p orbitals of two approaching atoms. Okay, now I forgot to mention this one thing. This is the type of overlap that takes place between the half filled s orbital of one atom and the half filled p orbital of the other atom. Now, what is the meaning of half filled overlapping? See, if the s orbital does not, the s orbital needs how many electrons? It needs two electrons. Every p orbital also requires two electrons. If you have a half-filled orbital, two half-filled orbitals are approaching each other. They're approaching each other and they're sharing the electrons with each other. Thus, what is happening? Their orbital is automatically getting filled up, right? Their orbital is automatically getting filled up. So, if z-axis is chosen as the internuclear axis, no overlapping can take place between the s and the px-py orbital or the px and the py orbitals. Okay, so what is happening here? See, if you have in if the z-axis is chosen as the internuclear axis, no overlapping can take place between the s and px or py orbital or px and py orbital. So basically what has happened, this is how the orbital actually looks like. Okay, I'm just going to draw this like this. See, you have, wait, this is the, let's call it py. Okay, this is the px and I'm going to draw the pz like this. Now, if the pz and the pz are going to overlap with each other, if the pz and the pz are going to overlap with each other, then the other two cannot overlap. Okay, so basically there is a distance like this. So if a pz of one and the s of the other are overlapping, then s cannot overlap with the y and the z. That's gone. Okay, there is only space enough for one overlap. If you want to overlap the py or the px, you have to have that in the internuclear space, internuclear distance. Okay, so until and unless you have that, you cannot have these overlappings participating in your bond formation. So again, I'm going to tell you, if the z axis is chosen as the internuclear axis, that is, if the z orbital is actually participating in the bonding between the two nuclei, between the two atoms, then the px and the py cannot participate, they cannot overlap because they are far apart, right? Look at this, they're far apart, right? The px and the py cannot overlap because the Z is already overlapping. Can you see? If the Z is not overlapping, the same goes for any other type of bond. Okay, can you understand this, Drupad? This is the yeah, this is the Z positive. This is also the Z positive. My hand is also the Z positive. So basically, what is happening? I'm overlapping like this. So these two orbitals will not be able to overlap with each other. Okay, there won't be a head-on overlap between them. Now, what else? The pi bond. Okay, you cannot have a head-on overlap between the py and the px if we take the z-axis as our default, but they can have something known as a sideways overlap. Okay, when the atomic when the atomic orbitals overlap in such a way that their axis remains parallel to each other and perpendicular to the internuclear axis, the bond formed is called the pi bond. Okay, now look at this. If the z orbital is taken as the internuclear, z axis is taken as the default axis, then this will be the px, right? This can be considered to be the px, this can be considered to be the py. Again, look at me. This can be considered to be the px and this can be considered to be the py, right? So another orbital is here. So what can you do? You can have the px overlap sideways. There is a sideways overlap that is possible. Okay, here also the py can have a sideways overlap. Okay, look at this. This is known as a sideways overlap. The orbitals formed as a result of the sideways overlap contains two saucer type charged clouds above and below the plane of the participating atoms. Okay, so let's see. If you have a z orbital like this, another z orbital like this, okay, this is known as the sigma bond. Okay, this, let us call them px and px. I'm only interested in showing you the px. Okay, this is the pz, the pz orbital. Okay, now this px and px can have a sideways overlap like this. So what do you see? You see an electron cloud. This is the sigma bond, Drupat. This whole region is the sigma bond. So there is an electron cloud above the internuclear bond and below the internuclear bond. Okay, the orbital formed as a result of the sideways overlap contains saucers. Can you see the saucer? See, this is the saucer, or you can say a kidney bean shape. A saucer shaped charged cloud above and below the plane of the participating atoms. So, Drupad, look at this. This is ideally known as the sigma bond. Okay, this is the sigma bond onto which you have one cloud above and another cloud below. Okay, this is known as what? The pi bond. Two such clouds make one double bond. Okay, now imagine this, Rupert. How many orbitals are present in the p subshell? There are three orbitals present in the p subshell. Am I right? So if you want to form a triple bond, the z and the z orbitals have to have a head-on orbital overlap. Okay, the px and the px need to have a sideways overlap. Now you may be thinking, sir, there is an electron cloud above and there is an electron cloud below. Won't that make it a double triple bond? No, it does not, because only one pair of orbitals is overlapping. If you want to have a triple bond, then the py and the py, there should be a bond here and here also. Okay, so these two make only one double bond. Okay, so you, for to make a pi bond, you need to have a head-on collision first. A head-on collision, that is a sigma bond, needs to be formed first, and then and only then can the two orbitals, the two rest of the orbitals can have a sideways overlap. Okay, so the pi bond is weaker bond as compared to the sigma bond due to this is a very important line, Drupad. The pi bond is a weaker bond as compared to the sigma bond due to the smaller extent of overlapping. In the formation of multiple bonds, double or triple bonds between the two atoms of a molecule, pi bond is formed in addition to a sigma bond. You can have a sigma bond without a pi bond, but you cannot have a pi bond without a sigma bond. Understood? The sideways overlap is only possible because two of the orbitals are holding on to each other as a sigma bond. Two of the orbitals are holding on to each other as a sigma bond. That is the reason why they are able to form the sideways overlap or the sideways pi bond. Clear? Understood this point? Clearly understood this? Okay. Now, comparison of the sigma and the pi bond. The sigma bond and the pi bond. The bond is formed by the end-to-end overlap. You can also call it the head-on overlap. Okay, that's what my teacher used to call it. The head-on overlap of the SS, the SP, and the PP orbitals along the internuclear axis. This bond is formed by the sideways overlap of the pp orbitals. Okay, so sigma bond can be formed between two s orbitals, two p orbitals, and an s and a p orbital, whereas a pi bond can only be formed between two p orbitals. That is one of the important points. Next, an overlap takes place to a great extent, hence the sigma bond is a strong bond, whereas the overlap is very small compared to that of a sigma bond. Lesser the overlap, less strong is the bond. Okay, so basically if you are holding each other like between two fingers, this bond is weak, but if you're holding them with both the fists like this, then the bond is very, very strong. Why? Because there is a larger overlap that is taking place in this arrangement as compared to this arrangement. Understood? So the overlap takes place to a smaller extent, hence pi bond is a weaker bond. Free rotation of the sigma bond is possible. Now, what is free rotation? See, if there is a single head-on overlap, see, let us imagine that these are the bonds between this is one structure, this is the other structure. There is a sigma bond that is taking place between these two structures. So, can I rotate them like this, Drupad? I can, right? Because there is only one axis, right? I can rotate it like this. Okay, so the rotation is possible in the case of a sigma bond, whereas free rotation around the pi bond is not possible, because now when you are having a pi bond, you are not only having one point, you are having a sideways overlap here and a sideways overlap here. Now if you try to rotate one molecule, the other molecule will also have to correspondingly rotate along with it, because there is a bond here, there is a bond on top, and there is a bond on bottom. But when there was only a sigma bond, you could independently rotate these two molecules like this. Okay, this was the rotation that you saw when you only had a sigma bond. But in the case of a pi bond, what happens? Both the molecules have to rotate with each other. Okay, there is the free rotation that the atoms enjoyed inside a molecule has now been reduced to zero because of a pi bond. Clear? Can you imagine this? You can imagine this, right? Okay, next. In this case, the electron cloud is symmetrical above the line joining the two nuclei. And in the case of the pi bond, the electron cloud is unsymmetrical. Okay, you have a symmetric cloud formation, and in the pi bond, you have an unsymmetric electron cloud formation. Okay, symmetric and unsymmetric. So, what are the various types? What are the various differences between the sigma and the pi bond? In the case of a sigma bond, you can have a bond overlap between the ss orbital, sp orbital, and the pp orbital. Whereas in the case of pi bond, you can only have an overlap between pp orbitals. As overlap takes place to a greater extent, hence sigma bond is a stronger bond, whereas a pi bond is a weaker bond due to lesser overlap. Free rotation is possible, free rotation is not possible, and there is a symmetry in the case of sigma bond, whereas there is no symmetry in the case of pi bond. Okay, unsymmetric in nature. Now we come to the most important topic that I've been waiting for: hybridization. Okay, when two different atomic orbitals join together to form a new type of orbital altogether is known as hybridization. Okay, now this concept was put forward by Pauling. He suggested that atomic orbitals mix together to generate a new set of equivalent orbitals called hybrid orbitals. Now, we know that different orbitals have different energy levels, right? S has the least amount of energy level because it is closer to the nucleus. The P has more energy level. The D has even more energy level. And the F electrons are the more energetic electrons inside the atom. Now, what happens when you hybridize two orbitals? When an S and a P orbital hybridize, then the hybrids, the result of your experimentation, the result of your hybridization gives you two orbitals having the same energy level. Understood? So that is what hybridization is all about. Now, so he suggested that atomic orbitals mix together to generate a new set of equivalent orbitals. Okay, or orbitals with the same energy levels, the same structure. Equivalent orbitals called hybrid orbitals or hybridized orbitals. These orbitals are used in bond formation. Okay, they are used in bond formation. This phenomenon is known as hybridization. Okay, so when you mix or intermix two different types of orbitals, okay, to create a new species of orbitals, you call it hybridization. It can be defined as the process of intermixing of two orbitals of slightly different energies so as to redistribute their energies to generate a new set of orbitals having equivalent energies and shapes. So, what happens here? Ideally speaking, these two energies, these two orbitals, when they come in contact with each other, what happens? There is a small nervousness that is happening. Okay, because these orbitals have different energies, the bonding becomes a little bit, what do you say? It's not balanced. Okay, but to overcome this, what are you doing? You're trying to create a new type of orbital for the same. Orbitals are required for bond formation. Even the hybridized orbitals are going to be used for the bond formation only. Okay, nothing else. So, when one 2s and three 2p orbitals of carbon hybridize, they result in the formation of four sp3 hybrid orbitals. Okay, so Drupad, how many orbitals participate? How many orbitals participate in the hybridization results in the number of hybrid orbitals. If one s and one p orbital hybridize, you get two sp orbitals. One s and two p orbitals combine, you get sp2, three sp2 hybrid orbitals. If one s and three p orbitals combine, they all combine together, you get four four sp3 hybrid orbitals. Understood? The a number of orbitals that are actually participating in the hybridization will result in the number of orbitals. The number is going to be the same. Are you able to follow with me? Okay. Now, the salient features of hybridization. The main features of hybridization are as follows. The number of hybrid orbitals generated and the number of atomic orbitals that are hybridized are equal in number. That's what I was trying to say. How many orbitals participate in the hybridization will give you the same number of hybrid orbitals. Now, the hybrid orbitals have equivalent energies. So, see, look at this. 1s and 3p orbitals, they combine to form 4 sp3 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 and sp3, four hybrid orbitals. And the fun thing is basically that all of them share the same energy levels. Everyone, every single four hybrid orbital, okay, is going to share the same energy level. Now, why is this more important? Ideally speaking, when you had the Vesper theory, you were bonding some of the atoms with the s orbital and some with the p orbital, due to which what was happening, due to which you were having some sort of what do you say, um, unsymmetry. Okay, like the s orbital has a lower energy level and the p orbital has a higher energy level. So some atoms would combine with a lesser energy level orbital, some would combine with a higher energy level orbital. But in the case of hybridization, every single atom is going to get combined with the same type and same energy of the orbital. For example, when you talk about methane, CH4, the carbon is attached to how many? Four different hydrogen atoms. Now, in the olden case, you would have had what? Now, what is the electronic configuration of carbon? 2s2, 2p2, right? So, if you were to consider the Vesper theory, then what would have happened? You would have to take two electrons from the s orbital and two electrons from the p orbital to actually participate in the bond formation of hydrogen. But that is not feasible because s orbital's energy is at a lower energy level, p orbital's energy is at a higher energy level. You would have actually had hydrogen atoms having different bond lengths, having different bond enthalpies. Okay, and that is not something that we are observing. That's not. So basically, instead of having two s orbitals and two p orbitals actually participating in the formation of the bond, what did you do? What did you do? You created four. This is also sp3, 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 and sp3. You created four sp3 orbitals to actually do the job for you. Understood. Now all the bonds have the same length, all the bonds have the same energy, okay, and you get a perfect tetrahedral geometry. Clear? Okay, now next, the hybrid orbitals are more effective in forming stable bonds than the pure atomic orbitals. This is what I'm trying to tell you. Okay, hybrid orbitals, because of the equivalent energy levels that they have, because of the same energy levels that they are better. They are more stable in forming bonds. Clear? Okay, these hybrid orbitals arrange themselves in spaces in such a direction so as to minimize repulsion between the electron pairs. So, the problem that we were having in the valence shell electron pair repulsion theory is now to some degree solved by using hybrid orbitals. Okay, so the hybrid orbitals take the shape of, they arrange themselves in such a way, they arrange themselves in such a way so as to create the least amount of repulsion. Always. Okay, now, therefore, the type of hybridization indicates the geometry of the molecule also. For example, an sp hybridization. Okay, we are going to discuss some of the hybridizations in this chapter. You have the sp, you have the sp hybridization, sp2, sp3, sp3d, and sp3d2. Sp hybridization is called a linear hybridization. Sp2 hybridization is called a trigonal planar hybridization. Sp3 is known as a tetrahedral hybridization. Sp3d, depending on what type of arrangement you have, you can have either sp3d or a dsp. Uh, I think sp3d or a dsp3. Okay, so you can either have a trigonal bipyramidal structure or an sp3, 1 2 3 4, yeah, trigonal bipyramidal or a square pyramidal structure. depending on what type of hybridization you're actually occurring. Okay, now we will discuss more about this in later. And sp3d2 is the octahedral structure. Okay, sp3d2 gives you the octahedral geometry that we have always seen, sf6. Okay, sf6 gives you the octahedral geometry. Now, important conditions for hybridization. There are some necessary conditions which are required for hybridization. Okay, let's discuss these three. Now, only valence shell orbitals of an atom take place in hybridization. For example, in the case of carbon, what are the valence orbitals that we have? We have the 2s2 and the 2p2, right? The 2s and the 2p are the two orbitals that we have now in the valence shell, and they are the ones that are going to participate in the hybridization. Okay, only valence shell orbitals of an atom take part in hybridization. The orbitals undergoing hybridization should have equal energies. Okay, once you have created the hybrid orbital, then what happens? Just one second. So, types of hybrid orbitals. Wait. Yeah, some important conditions. Now, one valence or only valence shell orbitals of an atom take part in hybridization. The orbitals undergo hybridization should have almost equal energies. The promotion of electron prior to hybridization is not necessary, and it is not necessary that only half-filled orbitals involved in the hybridization. In some cases, even filled orbitals of valence shell can also involve in hybridization. So both partially filled and completely filled orbitals can participate in the hybridization. Now, promotion of electrons prior to hybridization is not necessary. Promotion means what, you know? Huh? Taking an electron from the lower energy level and pushing it to a higher energy level. You are promoting it to a higher energy level. We are going to see more about this in the coming classes. Okay, how the various types of electrons are rearranged when you have hybridization take place. Now, what are the various types of hybridizations that are taken? Basically, I think you have the sp, you have the sp2, then you have the sp3. Okay, sp2, sp3, and the sp3d and sp3d2. That's it. Okay, that those are all the hybridization that you're going to learn here. You're not going to learn other fancy hybridizations. Okay, now, so there are many types of hybridizations involved in sp and d orbitals. The different types of hybridization are as follows. The sp hybridization, it occurs when one s and one p orbital mix together and result in the formation of two equivalent. So how many orbitals actually participated? Two orbitals participated, one s and one p. So the result will give you two sp hybrid orbitals. Okay, now results in the formation of two equivalent sp hybrid orbitals. Each sp hybrid orbital is associated with 50% s character and 50% p character. Now, think about this, Drupat. You have one s and one p. Both of them are coming together to actually form the sp hybridization. Okay, both of them are giving 50% of their effort, 50% contribution by both the orbitals. Therefore, in an sp bond, you have 50% s character and 50% p character. Okay, since both of them are participating with equal efforts, you have 50-50 s and p character that is present in the sp orbital, sp hybridized orbital. Now, such a molecule in which the central atom is sp hybridized are linked directly to other central atom have linear geometry. Okay, so an sp hybrid orbital geometry is always going to be a linear geometry. This hybridization is also known as diagonal hybridization. What is the sp hybridization known as? It is known as the diagonal hybridization, sp hybridization. Okay, now you had an s orbital. Now Drupad, with respect to the s and the p, can you tell me which orbital is directional and which orbital does not have any direction? S is non-directional, P is directional. Very good. Okay, correct. Very good. Now you have the S orbital and the P orbital. Now, when you combine the S and the P orbital, this is how the arrangement goes. Okay, so when you're going to draw this sp hybridized orbital, we'll draw it like this. Clear? So this is the sp hybridization. The negatives are inside. Okay, and the angle between the two is going to be 180 degrees. Clear? So this is the structure of an sp hybrid orbital. We'll learn more about this shortly. Okay, next, BeCl2. BeCl2 is what? Beryllium chloride. Beryllium has how many electrons in its outermost shell? Hydrogen, helium, lithium, beryllium. There are two electrons that are present in the outermost shell. Now, what happens here? The ground state electronic configuration of Be is 1s2, 2s2, right? 1s2 and 2s2. Continue. Now, in the excited state, one electron from the 2s orbital is promoted to a vacant 2p orbital. Now, I'll show you both the ground state and the excited state configuration of electrons. This is how you're going to draw them. Okay, let's look at this. So, you have, this is the 2s, 1s, and this is what? 1s, 2s, and 2p. The electronic configuration of beryllium is 1s2, 2s2, 2p, 0. Okay, now we are not interested in any other orbital apart from the valence shell orbital. Only the 2s is present. So ideally speaking, in the ground state, this is how the arrangement goes. But in the excited state, this is the ground state. Okay, but in the excited state, what happens? One of the electrons from the 2s actually jumps into the 2p orbital. Okay, one of the electrons from the 2s is going to jump into the, this is 1s is completely full. This 2s becomes 1, and one of the electrons jumps and goes into the 2p orbital. This is what I called promotion. Okay, promotion of an electron is taking place. To form the sp hybrid orbital, you require an s and a p, but unfortunately for you, there were no p electrons present. So what did you do? You had to promote an electron from the s orbital to the p orbital so that the p orbital could participate in the bond formation. Clear? Drupad, when it becomes overwhelming, please let me know. Okay? Yeah. So what is happening here is the one electron from the 2s is actually jumping into the 2p to have a promotion. Now, the ground state electronic configuration of Be is 1s to 2s2. In the excited state, one electron from 2s orbital is promoted to the vacant 2p orbital to make it bivalent. Okay, now what happens next? Now, one 2s and one 2p orbital get hybridized. Okay, now you are having one 2s and one 2p orbital. Now, both of them are going to get hybridized to form an sp hybridized orbital oriented at an angle of 180 degrees. Okay, now we know this, right? Sp orbital, the angle between the two hybrid lobes is going to be 180 degrees. Each of the sp hybrid orbital overlaps with the 2p of the chlorine axially and form the BeCl sigma bond. Okay, so this is how it's happening. This is basically, you are having the sp hybrid orbital. This is one sp hybrid orbital. This is the other sp hybrid orbital. Okay, the second sp hybrid orbital. Both of them are participating in the formation of bond with the Cl, chlorine. The basically we know what is the electronic configuration of chlorine: 1s2, 2s2, 2p, 2p6, 3s2, 3p5, right? So there is only one electron that is required, and that one electron is going to go into the pz orbital. So that is why chlorine is bringing its pz orbital with itself. Okay, chlorine is bringing its pz orbital where it is lacking one electron, and that is going to go have an head-on collision with the sp hybridization of the Be, thus forming two sigma bonds. This is one sigma bond here, and there is another sigma bond here. So this is how you are forming your BeCl2. Clear? Am I clear, Drupad? Okay. So what happened here? One, see, beryllium did not actually have an electron in the p orbital in its ground state. So a promotion of an electron was required, and it did. It promoted one of its electron from the s orbital, the 2s to the 2p, to get basically two different orbitals. Now that two hybrid orbitals that you get is now going to participate with the bond formation between chlorine and itself. Okay, thus you're going to get the Be. So look at this. Look at the arrangement. It's so beautiful. You have the Be here, there is a Cl here, and there's a Cl here, and you're going to have 180 degrees in between. Clear? Done, Drupad? Okay. Okay. So it has been now C2H2, ethyne molecule. An ethyne molecule is formed when both the carbon atoms undergo sp hybridization. Okay, now ethyne molecule is a good example of an sp hybridization because it helps us analyze that not just the sp bond is going to overlap. Carbon has what? Carbon has two another p orbitals that are going to participate in the sideways overlap. Okay, this is very exciting. I'll show you. See, the C2H2 ethyne molecule. Now, an ethyne molecule is formed when both the carbon atoms undergo sp hybridization. It has two unhybridized orbitals, that is the 2py and the 2px. One sp hybrid orbital of one carbon atom overlaps axially with the sp hybrid orbital of the other carbon atom to form a sigma bond. Okay, now look at this. This is one sp hybrid orbital. No, this does not look good. Okay, this is positive, positive, negative, negative. This is one of the carbon atoms. Okay, now it is going to have, this is also positive, positive, negative, negative. So it has formed a head-on collision. Okay, so this is the sigma bond that we were talking about. This is one carbon here, this is one carbon here. So it has formed its first bond with each other. Now you need to form a triple bond. Ethyne is a triple bonded carbon atom, right? C triple bond, C, H, and H. It's an alkyne. Now, what is going to happen here? It has one unhybridized, oh, it has one unhybridized, the px here and a px here. Similarly, it has another unhybridized py along the z axis, sorry, y axis. Okay, so this is the what? This is the z axis. Okay, this is the z axis, this is the x axis, and this is the y axis. Okay, now what is going to happen here? One sp hybrid orbital of one carbon atom overlaps axially with the sp hybrid orbital of another carbon atom to form a carbon-carbon sigma bond. So you have officially formed your carbon-carbon sigma bond. Okay, wait. Yeah. So this is where you are forming your carbon carbon sigma bond. Okay, next, what is going to happen? Now you are left with two other, you are also left with two other hybrid orbitals, right? So every single carbon is now having two sp orbitals. So one of the sp orbitals of both the carbon atoms overlapped to form the first sigma bond. The second orbital is going to orbit basically with let's say hydrogen. Okay, hydrogen here and hydrogen here. So there is some overlap happening here, there is some overlap happening here. So this is what, this is hydrogen here, hydrogen here. Now the c oh, the c h h bond has taken place. Now this is what, this is the px, the px here, then you have py here. The px and the px are going to have a sideways overlap. Okay, the px and the px are going to have a sideways overlap like this. So one of the double bond has formed. Then similarly, I'll use a different color. The py and the py like this. Okay, the py and the py are going to have the bond formation here. Okay, here also the py and the py are overlapping, and then you have another bond here. Clear? So the blue bond, I'll just make it more clear. So the blue color bond was due to the sigma bond, that is the sp-sp orbital overlap. The red color bond was due to the px-px overlap, making it the first double bond. And the py-py overlap is represented by the yellow color. This is how you get a triple bonded ethine molecule. Is it clear, Drupad? Okay, let's move on. So one sp hybrid orbital of one carbon atom overlaps axially. Now look at this. Even the axis is also beautiful. Look at this. See, mm, here. Can you see the axis? This is the internuclear axis. Internuclear axis is where the z orbital, the what is it? The z orbital is actually overlapping. Okay. Now, while the other hybridized orbitals of each carbon atom overlap axially with the half-filled s orbital of hydrogen atom to form the other sigma bonds. Okay, so a sigma bond here, a sigma bond here, and a sigma bond in the center. The remaining two unhybridized p orbitals of both the carbon atoms overlap sideways to form the pi bond between the carbon. Right? Sideways overlap is taking place between the px and the py to form the pi bond. Thus, the triple bond present between the two carbon atoms in the ethane molecule is made up of one sigma bond and two pi bonds, as shown in the following figure. This is how there are multiple ways, multiple structures that can be used to represent the CH bond. Okay, it is all at the end of the day dependent on how you are comfortable. Some, like, see, basically if I were to give the exam in the half yearly or in the finals, I would try to draw them separately. Okay, that is my preferred method of drawing the sp-sp head-on collision bonds separately and the sideways bonds separately, and then showing them this structure. I'm not going to draw this structure, this is too hard. I would rather draw this structure. Understood? So, and I would also try to take different types of colors to represent the different bonds that are being formed. Okay. Now, sp hybridization, is there any doubt? Rupad, sp hybridization. Okay, fine. Okay, fine. Now, the sp2 hybridization. Now, after linear structure in Vesper theory, What was the next structure that we learned after linear? Tri, tri, trigonal, trigonal planar structure. So the sp2 hybridization is going to give us the trigonal planar geometry. Let's see how. Now, when one s and two p orbitals mix together, they result in the formation of three equivalent sp2 hybrid orbitals. For example, let's see the BCl3, boron trichloride. The ground state electronic configuration of the central boron atom is 1s2, 2s2, 2p1. In the excited state, one of the 2s electrons is promoted to the vacant 2p orbital. Now, when it was the case of beryllium fluoride, we promoted the electron from the valence shell to the valence shell only. That is, we took one of the electrons from the 2s2 and gave it to the 2p, right, to make it into a sp hybridization. In this case, to form an sp2 hybridization, we need to have one s and two p orbitals. But unfortunately for us, what is happening here? You have the 1s2, the 2s2, 1s, 2s, and the 2p. 1s has two electrons in the case of boron. 2s has two electrons in the case of boron. But for boron, the 2p only has one electron. So what do? You promote one of the electrons from here to here. Thus, what happens? You have the 1s2, you have the 2s2, and then, sorry, 2s1. I'm so sorry. It is not 2s2, it is 2s1. And the 2p, there will be one electron here and one electron here. Now, there are three electrons in three different orbitals of the valence shell. Okay, so you have one s and two 2p electrons. Okay, now in the excited state, one of the 2s electron is promoted to the 2p orbital. Okay, one of the 2s electrons is promoted to a vacant 2p orbital, so that boron has three unpaired electrons. Now these three unpaired electrons are going to produce three sp2 hybrid orbitals. These three orbitals, one 2s and two 2p, undergo hybridization to give three sp2 hybrid orbitals oriented in a trigonal planar arrangement. Three sp2 hybrid orbitals overlap with the 2p orbitals of chlorine to form the three BCl bonds. Therefore, the geometry of BCl3 is a trigonal planar structure with the bond angle to be 120 degrees. Now, this is how the sp2 hybrid orbital actually looks like. So you have the three positives here, 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 and the negatives are tucked next to the two axes. Okay, so this is how you have the sp2 hybrids in place. Now the three sp2 hybrid orbitals will now bond with the three pz orbitals of chlorine like this. Okay, a positive bond here, a positive bond here, and a positive bond here. Okay, positive bond here, positive bond here, and positive bond here, thus forming a trigonal planar arrangement. Okay, now in the trigonal planar arrangement of BCl3, what is happening? The lobes are what? They are 120 degrees apart, right? They are exactly 120 degrees apart from each other. Okay, so whenever you form a bond with them, they will always share the trigonal planar geometry. Understood? This is how you get the BCl3. Now let's look at an alkene. For example, you have C2H4. C2H4 is a double bonded carbon molecule. It looks like this. You have the carbon here one with one hydrogen here and one hydrogen here, one hydrogen here and one hydrogen here. Now, if I were to just highlight this portion, Gilbert, does this look like a trigonal planar geometry with one carbon and two hydrogens? And similarly, you have one more trigonal planar geometry. So two trigonal planar structures are used up, one next to another, to actually produce what? To actually produce the CH2 molecule. Now let's see what happens in the CH2 molecule. Now let's see. The C2H4 ethene molecule is the formation in the form. One second. Yeah. Okay. I think I can remove the charger. Okay. In the formation of an ethene molecule, one of the sp2 hybrid orbitals of one carbon atom overlaps axially with the sp2 hybrid orbital of the other carbon atom, thus forming the carbon-carbon sigma bond. Again, the three orbitals are there. Two of them, one from each carbon atom, are being used to form the sigma bond between carbon and carbon. Okay, carbon-carbon sigma bond is being formed like this. And then rest of the four two of each carbon atoms are basically going to form a sigma bond with the remaining hydrogen. Okay, they're going to form a bond with the remaining hydrogen. Now in the case of carbon, what was happening? You had basically let's look at the structure of electronic configuration of carbon. 1s2, 2s2, 2p2. Okay, so in this arrangement, what was happening? You had one box like this, one box like this, and three boxes like this. So 1s2, 2s2, then you have the 2p2. Now, there is an electron present in the s orbital, and there are two electrons that are present in the p orbital, right? So basically, you don't have to promote any electron to the p orbital for the hybridization to continue. So what do? You have from here to here, you have sp2 hybridization, but you have one orbital left behind. You have this one orbital left behind that can be used to do the sideways overlap. So we know that ethene molecule has a double bond, right? So one of the p orbitals can have a sideways overlap with the other p orbital of the other carbon atom to actually form the double bond. Okay, it is going to form the double bond like this. Clear? So let's actually discuss this in detail. Now, one of the sp2 hybrid orbitals was consumed in the formation of the carbon-carbon single bond. But the rest of the two hybrid orbitals are going to be used to form the sigma bond between carbon and hydrogen. The unhybridized orbital, either the 2px or the 2py of one carbon atom, overlaps sideways with the similar orbital of the other carbon atom to form a weak pi bond. Okay, it is forming one weak pi bond. Now, Drupad, again, I'm going to tell you this. Okay, you may say that, sir, there is an overlap here and there is an overlap here. This is not two different overlaps. This is one single overlap that takes place between the two p orbitals. Understood? So this is not a there is not a triple bond that is being formed here. Two sideways overlaps between the two lobes of the two p orbitals result in the formation of one pi bond. Understood? So you have, which consists of two equal electron clouds distributed below and above the CH bond. Okay, now this is where everything becomes more and more interesting. Now, in the case of sp2, what did you do? Sorry, in the case of sp, what did you do? You took one of the s orbitals and one of the p orbitals to form the to form the hybrid orbital, and the rest of the two orbitals were being used to form the triple bond. Okay, In the case of ethene molecule, one sigma bond is formed, and then you have one pi bond. Only one sideways orbital, a sideways overlap is required. Thus, we get one sigma and one pi, therefore a double bond. 1 sigma 2 pi gives you a triple bond. 1 sigma 1 pi gives you a double bond. Thus, which consists of two equal electron clouds distributed above and below the C carbon and the hydrogen atoms. Thus, in ethene, the carbon-carbon bond contains one sp2, one sp2 sigma bond, and one pi bond. The carbon-carbon bond length is 134. The CH bond is sp2s sigma with a bond length of 108. Thus, the the hydrogen carbon hydrogen bond angle is 117.6 degrees, while the carbon carbon hydrogen angle is 121 degrees. The formation of a sigma and a pi bond in ethene can be shown here. Okay, so you are having a sigma bond being formed here and a sideways pi bond being formed between the one unhybridized orbital that the carbon atom has. Okay, so the overall arrangement will look something like this. Okay, so you have wait. These are the three sp2 hybrid orbitals of both the carbon atoms. One here, one here. Now, what is going to happen? It is going to form a head-on overlap here. Okay, and you're going to have one hydrogen atom come here to form a head-on overlap, one hydrogen here, one hydrogen here, one hydrogen here, and then you have the final, the one unhybridized p orbital here, one unhybridized p orbital here, forming a sideways overlap, forming a sideways overlap like this. Understood? This is how you have the complete structure of the C2H4 molecule. Clear, Drupad? Is this perfect? The diagram. Okay. Let. Do you have any doubts till now? Okay, fine. Now, the formation of the sp3 hybridization. Now, in the case of sp3 hybridization, as the name suggests, you have one s and three p orbitals come together to form four sp3 hybrid orbitals. In the sp3 hybridization, what happens? You have one s and three p orbitals of the valence shell intermix to form four sp3 hybrid orbitals of equivalent energies and shapes. Each sp3 hybrid orbital contains 25% s character and 75% p character. Oh, I forgot to tell you about the s and the p character in the case of sp2. So in the case of sp2, you have 33.33%, 33.33% s character and 66.66% p character. Why? Because you required one s and two p orbitals to actually come make this sp2 hybridization possible. In the case of sp3, you have one s and three p. Therefore, the s character will be 25% and the p character will be 75%. Clear? That's how the percentage actually takes place. Okay, s character and the p character. There are some of the some nuanced questions are going to be asked regarding this section, okay, in the later chapters. Okay, huh? Because of the s character there is more electron uh, electrons are brought closer or something like that. A lot of theories, we'll discuss this later. Now, the four sp3 hybrid orbitals so obtained are directed towards the four corners of a rectangular tetrahedron. That is why you have a tetrahedral geometry in the case of sp3 hybridization. Okay, so the angle between the sp3 hybrid orbitals is going to be 109 degrees and 5 minutes. Now you have to remember the bond angles. And sp hybridization, the angle between the two hybrid orbitals is going to be 180. In the case of sp2, it's going to be 120. In the case of sp3, it's going to be your 109 degrees and 5 minutes. Next, the formation of the CH4 molecule. Now, unfortunately for us, unfortunately for carbon, it only has two electrons in the p orbital, but it requires it requires the participation of the three p orbitals. So what does it do? It promotes one of the electrons from the 2s to the 2p, so that all the s and the 3p can participate together. Now, formation of methane, CH4. In this, one 2s and three 2p orbitals of carbon intermix to form four sp3 hybrid orbitals that overlap with the 1s orbital of four hydrogen atoms to form the four CH bonds. Since the orbitals are directed towards the corners of a tetrahedron, the shape of methane is known as a tetrahedral geometry. With the carbon hydrogen carbon hydrogen, that is HCH bond, to be 109 degrees and 5 minutes. Now let's actually look at how the formation, oh, they haven't given us the formation. Okay, I'll explain to you what happens here. Now here we have what we have, the 1s2, that is two electrons here, the 2s2, the two electrons here, and the 2p2, that is 1 2. That's it. Now, this is known as the ground state. Now, in the case of the excited state, what happens? The 1s2 does not participate because only valence shell are allowed to participate. The 1s2 remains as is. The 2s1 and the 2p3. So, one of the electrons actually got promoted and it joined this one. Okay, one electron actually went from here and joined to the third one. So what happens here? Once again, okay, the form, yeah, it gets promoted. Now what is going to happen? All the four orbitals, this, and this, are going to participate to form the sp3 hybrid orbital. Clear, Drupad? And luckily for us, they take the four corners of the tetrahedron. Okay, fine. Now the formation of the ammonia molecule. In NH3, nitrogen is the central atom, right? Nitrogen is the central atom with valence shell, outer electron configuration, ground state, and its 1s and 3p orbital give the 3 sp3 hybrid orbitals of equal energy. Okay, what is the electronic configuration of nitrogen? 1s2, 2s2, 2p3, right? 1s2, 2s2, 2p3. Yeah, 4 plus 3 7. Yeah, so the s and the p orbitals are all ready. There is no promotion of electrons required. All the s and the p electrons are going to participate to produce the sp3 hybrid orbitals. Okay, so the three sp3 hybrid orbitals contains three unpaired electrons, whereas the fourth have a lone pair of electron. These hybrid orbitals having unpaired electrons overlap with the 1s orbital of a hydrogen atom to form the three NH sigma bonds. As lone pair bond pair repulsions are greater than bond pair repulsions, the molecule thus gets distorted and the bond angle reduces to 109 degrees, sorry, 107 degrees from 109 degrees 5 minutes. So Dilpat, we are having how many hybrid orbitals do we have? we have four hybrid orbitals. Now, the four orbit and from the four hybrid orbitals that we have, three of the hybrid orbitals are going to be used to form bonds with the three hydrogen atoms. Okay, and one of the hybrid orbital is going to be used to place in the lone pair of electron. Thus, the arrangement, the geometry is going to be tetrahedral. Okay, but in the valence shell electron pair repulsion theory, what do we call it? See, the there are four hybrid orbitals in the case of NH3. Okay, nitrogen is forming four hybrid orbitals. sp3, four hybrid orbitals are being formed. Three of these hybrid orbitals are being used to form the sigma bond between the oneness of the hydrogen atom. The fourth sp3 hybrid orbital is going to be used to basically localize the lone pair of electrons. Okay, the lone pair of electron that nitrogen has is going to be used to store in the fourth hybrid orbital. Thus, the arrangement may look as if it is a tetrahedral geometry, but it is not. It's not a tetrahedral geometry. It is what type of shape? What is the shape called? Trigonal. No, not bipyramidal. Trigonal pyramidal. Okay, it's going to have a structural shape known as trigonal pyramidal. Okay, so the lone pair of electrons is never considered in the actual shape. See, it's only going to have a trigonal. It's basically nitrogen here, a hydrogen here, a hydrogen here, and a hydrogen here. So there is a pyramid shape like this happening, and you this is how the shape is going to look like. Okay, so it will be a pyramidal shape, trigonal pyramidal shape. The geometry of such a molecule will be a pyramidal as shown in figure. Okay, so understood this, Drupad? So it is not a tetrahedral arrangement as in the case of CH4, because when we were talking about CH4, carbon, fortunately for us, did not have any lone pair of electrons, but nitrogen does. Nitrogen does have a lone pair of electrons. Now, because of that lone pair of electrons, the lone pair bond pair repulsion is going to arise. Therefore, it is going to reduce the bond angle between the hydrogen, nitrogen, and hydrogen from 109 degrees and 5 minutes to 107 degrees. Okay, it's going to reduce the bond angle. And since the bond angle has been reduced, we cannot call it a tetrahedral arrangement. No, we cannot. We can give it a name called the trigonal pyramidal structure. I hope it is absolutely clear. Okay, next. Hybridization of, you have to go now? Okay. Uh, Please read till where I have taught you. I think we can continue this in Monday, Drupad, okay? Because tomorrow I won't have any time. And please join in on Monday's class. I will most probably try to finish this chapter on Monday. Okay? So just give me 1 second for the outro. So students, we are gonna stop this class right now. Okay, and we are gonna continue this section in on Monday's class. I hope you really like the way I am teaching you. This is a very interesting chapter. Okay, it's not a hard chapter at all. Try visualizing it. Try seeing the animated videos of all the structures and all the others. And if you are asking, the book that I use is the Arihant All-in-One Class 11th. Okay, it's a really good book. That's from where I'm teaching you all the notes. Okay, so if you really like my video, please do like, share, and subscribe. And I will see you in the next class. Thank you so much.